Hey everyone, I'm going to run through some topics and questions that were missed on the last multiple choice for Unit 3. So we're talking about circular motion and universal gravitation. So one idea that I didn't really touch on in class, and I apologize for that, is the idea between inertial and gravitational mass. So what gravitational mass is what we get when we measure an object by placing it in a gravitational field. So that could be like putting a block on a scale and it reads that force that's being caused by gravity and it gives you a mass. So let's say the mass of this little block is 1.4 grams. Okay? So it's using some sort of scale that's oriented towards the center of the Earth using g as the acceleration. Inertial mass is measured by applying some force and measuring the acceleration and then using Newton's second law, which is force equals mass times acceleration. So let's say I had that same block, I apply some force, I measure some acceleration, and what I end up with is I find the same answer for the same object. And that's because experimentally, these two masses have been proven to be the same. So no matter if you measure the inertial or gravitational mass, you will end up with the same value. It's just a concept of how we find the mass that is different. So here is an example. We want to use a spring scale, and we want to measure the gravitational and the inertial mass. What are the necessary tools we need? So if we wanted to measure the gravitational gravitational mass, all we need is the spring scale, because the spring scale measures force. So I could just hang that object from the spring scale and it tells me a force reading or a mass reading, and I can figure out the mass. Okay. And then if I wanted to figure out the inertial mass, so I use that spring scale to measure force. I use my meter stick to measure distance and measure time with a stopwatch or a timer, and I can figure out the acceleration given that force. All right, so then the next one, two experiments. Which one, if either, can be used to find the gravitational mass? And only experiment 1, because we're measuring the weight with an electronic balance. Experiment 2 would be measuring the inertial mass, because we are pulling with an applied force. Next question was question 5, and those other two were 3 and 4, I believe. So this one was kind of an interesting question. So the only experimentally measurable external force exerted on a planet is due to the force of gravity from the star. Is the student's claim supported by evidence? What reasoning supports or contradicts the student's claim? So, out in space, okay, a planet is orbiting a star. That star has a ton of mass. It's going to exert a very, very large gravitational force. Okay. So, yes, he's correct, but there are some other tiny forces, like say there's another planet in that solar system, there's going to be a little tiny force because those two objects have mass, so they exert a force on each other, but it's going to be very, very small compared to that of the star and that force that's exerted on the planet. Okay, on to question 7. How does the magnitude of the gravitational force from planet Y compared to that of planet X on this satellite? So we're going to be using that universal gravitation formula, so G, mass of the planet, mass of the object, and distance squared. Note that the distance is 2r. It's the radius of the planet and that r distance above the planet to the satellite. And simplifying that, you end up with the force on the satellite for planet X is G just the mass of the planet, mass of the satellite, over 4r squared. Note for planet Y, the distance is 4y, and the mass is 3m. And so simplifying that, you end up with 3g, your masses, over 16m squared. Oh, that should be r squared. There we go. Okay, so everything about those two forces is equivalent except for the coefficient. So it's both, they both have g, the same two m's, r squared, but the coefficients are just different. So 1/4 times some value equals 3/16. And so those are just the coefficients for those two forces. So how many times greater is Fy than Fx? And if you solve for x, you end up with x is 3/4. So I have to take the force for planet X and multiply it by 3/4 to get the force on planet Y. Same problem. Well, same scenario, different problem. This is question 8. So planet X and Y, now we want to know how does the gravitational field on X compare to that of Y. So on the surface, we can set the weight, mg, equal to the gravitational force, which is that big universal gravitation formula. The mass of the object doesn't matter, so then you end up with g equals gm over r squared. For planet X, the mass is m, the radius of the planet is r, so that is your value for g on X. Do the same thing for planet Y, and you end up with g on Y is 1/3 of what it is on planet X, so g of x equals 3 times g on the planet Y. Right, an Atwood's machine on a mystery planet, we want to figure out what quantities do we need to find g. So if we set up, look at our forces. Okay. So we've got tension acting on both blocks and the weight acting on both blocks as well. I know which direction it's accelerating, so I can use that system formula. So net force equals total mass times acceleration. My force that's causing the acceleration is positive. That's the m1g. And then m2g is resisting, so that's a negative force. That equals the total mass times the acceleration. And I went through and solved this for g, which you didn't need to do. You just needed to note that you needed mass 1, mass 2, and the acceleration to find g. I don't know what's going on here. Okay. Next slide. Okay. So a ball being swung around a circle. I want to solve for centripetal acceleration. So at the top, sum of forces equals ma. Remember that things that point towards the center of the circle, so this is the top, the center's down here, those are both positive forces. Okay. At the bottom, so it's going like this, that's awful, like this. This is going to be a negative force, and up here this is a positive force. Okay, so again, setting up that sum of forces at the bottom equals ma, that's centripetal A. Tension minus weight equals ma. And I solved both of these for Fg because I don't need it. Okay? I don't want that in my final answer. So what I can do is set those two circled quantities equal. And all I'm doing now is solving for acceleration. You end up with T2 plus T1 over 2m. Right, we want to figure out the inertial mass. So that, remember, inertial mass, I want to use an applied force and measure an acceleration. So I need an accelerometer and a force sensor.